Hello, ladies and gentlemen. Now, today I'm going to go ahead and talk about the Guacanayabo Impactor. So, it's one of the two extraordinarily largest impactors on our planet. The other one, that looks almost just like it, is the North Pacific Oceanic Impactor. So, I'm going to show you this one today and talk about this, and then a little sneak preview. We're going to talk about the Hawaii, or no, wait. I wanted to call it the Hawaiian Impactor. Believe it or not, yeah, it's a whole nother story, but Oahu is actually, it's actually between Oahu and some other island. So it's actually an impact crater. I was surprised at that. I thought more that like it would have been the earth swelling and burping or something, but apparently I was wrong. So it'll be really exciting to check that out to understand that where the Hawaiian Islands came from. They actually were created by this impactor. Don't think that these impactors cannot create land. And so if that's the case, then that land would have come up from the ocean floor, which means that a lot of the material around our planet could be continental, lighter material and still be held deep below other surfaces. And then it re-emerges when it's let loose, something to that effect, right? So right now we're looking at Google Earth, and we're looking at the Guacanayabo Impactor. There are several impactors in this region, and when the artillery fires onto targets in a small area, we call this a converged sheaf because they are converging into one type shot group. So the series of impactors we have in this region down here with the Caribbean Sea, they're all very, very, if you were to sit there and be a soldier shooting at a target, you'd be really excited about how close you kept that shot group. You're like, oh, I'm awesome! Alright, get that expert, whatever the hell it is, and I can't remember, what's it called? That little flashy thing you put on your chest. Anyway, it goes, you see this little round circle here? Yeah, there's a bunch of those right in here, and one of those is, Chicxulub, you got it right. But this guy here may or may not have actually been related to Chicxulub directly, or it may have. So here's the theory, right? If this impactor struck, it obviously struck first because it was the meanest one out there. So let's say it struck the Earth and then it blows all of this astroclastic, and I made that one up, I did, pyroclast, based on pyroclastic, garbage up into the air. Say, for instance, the blast is so great that it pushes that material up into like the thermosphere or somewhere out where it's not too far out to get pulled back into the Earth. And then as it comes back raining onto the Earth, it comes back in a bullseye because it's coming straight down onto the surface. Deflection at this point may not necessarily have enough time. The atmosphere doesn't have enough time to deflect the object as it re-enters our atmosphere, and then it strikes the Earth dead on, and that gives you these nice perfect little circles, a lot of the time what we see on the moon. So that's a possibility, and this explosion here would have occurred after this one did, to an extent, and that's how we know. And so Mexico was here just like it is when this guy impacted the planet. And that we know because I can follow the blast ring through here. The blast ring gets a little more shady up around over here, and certainly gets shady over here, which is what leads me to believe that the Bermuda Rise impactor, that's the Bermuda Rise, that little speck right there, that zit, the planetary zit, that is. Yeah, our planet really needs to start washing itself, right? So there it is, right? And so that one kind of erased a lot of good information we could have probably had out here. That's the impression I have currently. I don't always see all of the things that I need to see to be able to determine who clobbered us first. And it seems that we might have some evidence down in here. We do have evidence with the curvature of the Dominican Island kind of ridge thing here, and as it bowls around and then it follows right up through that island there and up this way. So you get a pretty good idea. This is probably the greatest blast ring from this particular impactor. Now, as large as it was, it could have been even larger than that. However, that's when we start getting into our 60-degree global distortion. Excuse me, my ear itches. I'm sure it doesn't bother you to watch me scratch my ear. I don't. You wouldn't see a newscaster, do you? Well, the weather over here in the corner. Yeah. Anyway, I was looking at my finger to make sure I didn't have any left on my finger. Actually, it's water from the bath. That's what it is. Okay, now that we've done talked about all that, I know old people are gross. At least that's what the young girl said at work. I thanked her for it. I was like, well, thank you. That was a nice thing to say. So, here's the deal, right? These two yellow lines, like the galactic Tropic of Cancer and Tropic of Capricorn, as I like to call them. That's our galactic plane. So, the Earth's galactic flight posture keeps the North Pole slightly above that plane. You see that? This is actually the center of that plane off of Sunrise Point. So the North Pole is more than 1.5 degree up. We can see that here. I got the 1.5 degree based on the axial tilt and axial cant of the solar system and all that, and as it should have been in relation to the galaxy. But the truth of the matter is, this is the measured plane for the galaxy, and it's inarguably correct. So my determination of the degree of offset for the North Pole is actually not correct. This is more correct. However, when this impactor struck the Earth down here in Guacanayabo, it didn't exactly. It may not have struck the Earth when the Earth was at this current flight posture. Okay, the Earth's North Pole may have been at a different location. And so each time one of these great big massive rocks, by the way, this one was measured at about 56.6 kilometers in diameter. You see that little red dot up there? That is your 56.6 kilometer diameter impactor size in relation to the NPOI, or the North Pacific Oceanic Impactor, up here. And why did I put it up there and leave it on? Well, because when I traced this guy, I'm going to show you later, when I traced this guy's B2W wings, I clicked, dragged, and dropped it right over here, oriented it to this particular wing spread, and remarkably, it's almost like they were twins. The only thing that separates them from being twins is that this guy came from an entirely opposite poo than the NPOI. So where the NPOI struck us like on a head-on collision, bam, this guy came up and struck us from behind. So here's the thing, right? Our solar system rides the wave like the albatross, up and down. So when we're up at the top of the crest of our SMEGA wave, supermassive electromagnetic gravity wave, the sun is most agitated up at the top because it's got a lot of turbulence up there, just like any riptide wave you see on the ocean, or rather on the shore, right? And it's going up there, it's getting pissed off because the wave is irritating it. So every 11 years it gets irritated like that. And then the solar system floats down and gets into the middle area. We're going to talk about the middle area. And then it hits the trough of the wave down here at the bottom. So when it's at the trough of the wave, we're in the sun's solar minimum cycle. So basically, our solar system, in the distance our solar system is from our parent black hole, the wavelength of our SMEGAs from our parent black hole or maybe I should say is 11 years. At that distance we are from the center of our galaxy. You see that? So if we were further out, then the wavelength would increase. Okay, now, why am I telling you guys that? Because it will be during the solar minimum when the Earth is at its highest risk of being struck from behind. Why is that? Because, like in rivers, you have a lot of rapid current and agitation on the top of the water that you can see. But down below, you have some huge current going. That's where the greatest current is actually being carried. And that's how it ends up taking and dragging people underneath and getting them stuck under objects or, obstacles under the water where they end up eventually drowning. So it's kind of the same thing. We don't want to drown. We want to stay up in the virga. And but we can't because we're floating on that wave. But when that wave dips us down, it's getting us closer to the galactic plane or the galactic equator. And when it does, that stuff down there is flying out a lot faster than we are. And because we're just like floating at the top of the wave, and that stuff is going down here it's like, a really slow car getting onto the freeway when everybody's just going, right? Well, that's what's happening. And then we get too close, and one of those guys, them little stragglers out there that's just at a slight offset from its trajectory that it should be on, it comes out and clobbers us, catches it, bam, right in the rear end. Well, funny thing with this rear impactor that caught us from behind, it didn't hit the rear end, so it had a much different effect on our planet. So here's our planet like this, and it's flying through the galaxy with the nose up, right? And then you have this impactor that comes up from this direction here. Well, what happens when you have something hit the nose of something else? It pushes it up. So then you push it up, and then it explodes, and then you got this. Boop, 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 boop. Now we have a flat tire planet. It starts doing all kinds of crazy stuff, and that's when we start to come down here, and we want to look at Earth's second stripes. Don't necessarily follow the title on that because that's not relative, but likely to change based on my continued theorizing of what in the world happened when, right? But I'm associating these stripes with this particular impactor because it makes sense. These stripes, unlike all the other stripes that I've mapped, it wasn't until after I finished mapping these that I realized they came out like an oblong or an oval. And ladies and gentlemen, that kind of tells a story. So if you have this oval where you have the length going from here to here, that's about where this impactor would have hit. So that would have been your form of going up and down. So all the scientists that are watching me that don't believe that I know what an impact site looks like, you might want to reconsider what the planet is telling us in this particular instance, and I might not be so wrong after all. The funny thing is when it starts to rock up and down this way, it's rocking like this as it's rotating through the, it's like, wow, bam, got hit hard, right? And then you go down here, and it's kind of like, it looks like it's going the other way. So our planet is like doing this weird thing. I don't even know if I can do it. I mean, if you can have all the other stuff anyway. So now the story is, back in the day, Antarctica and Australia were once a part of the same continent, which would have been, and this is totally not with our stories of history on Earth at this current moment, but I'm going to stick by my guns. And they were once the same continent. That's why you're finding so many super old rocks on Australia, because after all, our South Pole cooled first before any other part of the planet did, and it was cooling faster. And so it had the continental mass that was heavier than all other continental masses on the planet, settling at the base of the planet. But when this Guacanayabo Impactor struck the planet couldn't balance itself anymore, and it broke the continent. So that after that, Australia became loose, like you see the icebergs coming off of this continent, and it started migrating toward the equator because of centrifugal force. All right, and so as it's doing that, and you notice this is the direction our planet rotates. I can't really rotate it. I can if I don't want to do that. It's going like this, right? So you have the 19. I'm looking at the clock, 3:19. I have a little time. So you have the what's that? The coefficient of solar wind pressure drag that's also causing Australia to not only migrate toward the equator but move toward the west. So it's coming up. So you see this little squiggly stuff here. Now this squiggly stuff here was created later, but it was more of a fluid movement by Australia separating from this area here, and and then once the two continents separated, that was when on Antarctica was free to rotate as you can see it rotating with its 4 spiral density arms. All right, now that means that more than likely these two guys, if this 11 stripe mapping is telling us that the South Pole was here, these guys broke away from this point here. However, if that's not the case, and the Earth is balanced with Antarctica here and Australia here, then it could mean that before these stripes were engraved in the surface of our planet, the South Pole might have been more like between these two, and it would have been, and Antarctica would have been over here, and then as that impactor struck, it knocked the planet clean off its axis. That's what knocks the planet off the axis, not just freak days when you wake up and the sun's rising on this other side of your house. You don't have to worry about that. The general migration of our axial tilt and such in the North Pole is so minute and so slow. It's doing it every day, and it takes eons to frickin' go anywhere. Okay, it's when you get clobbered by something like this where you have a traumatic change in your axial tilt and axial cant. And of course, as we can see right here, your precession gets really wild. Now, we don't see that kind of evidence going on with the North Pacific Oceanic Impactor, okay? And it pretty much is so close to the same location as our current North Pole when it impacted that its Jupiterian stripes are pretty much in the same orientation. All right, now, the Dominican Islands down here were not created by this impactor. This impactor, I'm pretty sure, had to have struck before this wave came through. And I'm still not quite sure who created all this, the Yucatan Peninsula and this stuff right here. Not positively certain. I'm working on that. Not everything reveals its secrets to me right off the bat, and sometimes I have to go back and reevaluate. But I'm really close. I am very close. But I can almost tell you that, well, these are the wrong stripes. But if you look at Hawaii over here, when the Hawaiian impactor struck here, it probably was more likely responsible for creating, either it was responsible for creating the, but maybe not, because here's your striations for the today's current Jupiterian stripes. And that means that Hawaii's impactor more than likely, had it occurred during this period of our Jupiterian 9-stripe period, the energy would have gone this way, but it could have gone this way and traveled down until it found a weak opening, like we see when actual tsunamis hit the shorelines and then get channeled. All that energy gets funneled into a small tight space and channeled right up our rivers. And it's even more devastating than what it was when it was in the ocean. So it seems. So that's what you get when you get over here. It gets channeled. You got the same thing down here with the South Sandwich Islands. This energy was brought this way and then channeled through between these two continents and came through and created this asthenospheric tsunami. You see how that works? You still don't believe me about these tsunamis? What's going to happen is nobody's going to believe me, and then when it's too late, it's too late. We'll be lucky if there's one of us left alive That's how horrible these things are. I mean, look at the damage that the South China Sea impactor did to our entire planet. A whole hemisphere of damage. And when you look at all the waves, you got them all coming down from this very same point here, all over the North American continent, down this way. And when you look at them all traced, this whole entire hemisphere melted in a geographical sense. And this stuff here flowed so far, it almost flowed the entire distance all the way down. Well, it did flow the entire distance all the way down to the South Pole, short of this point right here, right? So that impactor created New Guinea, it created Fiji, and it created New Zealand. That impactor wasn't even as big as the NPOI or the GI. GI over here is the Guacanayabo Impactor. So velocity. So we're talking about velocity. So chances are with these larger impactors, they might have been more spherical. But if you have one that's a flying Volkswagen, say for instance you have Apophis. If Apophis enters our atmosphere and it's end to end, oblong, and it's rotating on its shortest diameter, okay, like a bullet, it could probably have a much, much higher magnitude than, say, for instance, it's going head over heels. That's, believe it or not, that actually is what it sounds like. I have really been there when that sounded, you know, flying Volkswagen. That's when the round lost its freaking fin. And you're just like, well, hope it doesn't drop right here. Yeah, keep going, buddy. Well, sometimes rocks coming from outer space do the same thing. Not that they ever had fins. So there's what you got, right? And that's pretty much everything in a nutshell. And I told you about it. This one most likely being the one that separated Antarctic Australia, and so that's how you know that Australia was already here when this guy flowed down and hit Australia basically, and then we got redirected back and around all the way down to the, yes, that is correct, bottom of the planet. Bottom. Even though the planet flies like this, I know it's kind of hard to believe, because you think bottom means this is the top, this is the bottom. No, in space it's different. In space we're looking at the bottom this way. So you have the top on the side over here, and you have the bottom on this side over here. And that's how it works, because you have a greater force of gravity striking this side of the planet. And this is the side of the planet that's going like a drill through the galaxy forward. You see that? You see how that works? All right. So, oh yeah, I was going to go down here. So I have a little bit of time left. This is some of that stuff. So here it is. I traced that guy right there. I put it down here. Oh my gosh, look at that. At first I was thinking it was bigger anyway, but it had the same arc as far in terms of this portion of the round itself, and the round in the line, and the B2W wingspan. And then we come down here, I measure this to the distance from the pop to the B2W for the GI, and then I come down, this is my closer thing, it's telling us 0.23 inches, 0.23 inches, okay? In PowerPoint, you go by inches, not anything else. So here we measure the pop to the B2W on the NPOI, and I'm going to come down here, and this is what I get, 0.22. So you see, this guy is barely smaller than the other one. They're almost exactly identical. It's amazing. I don't even know how that is possible. But then I was like, wait a minute, let me just move this down a little bit. Look how close that is. It's like they not only were almost exactly the same size, they also came in at almost exactly the same trajectory. All right, and we're going to keep going down right here. And so this was my first estimation, and this blast ring was definitely not the one. I'm pretty sure this is the one that was ended up too large. Yes, it did, because if you don't catch the correct ring, you have to measure blast ring number 1. So I ended up having to go back in here and look for blast ring number 1, because this one obviously was not blast ring number 1. Not after I calculated the trajectory, because the trajectory that I had calculated at this point was telling me that it was a low angle impactor, and I know for a fact with a B2W fan like we get up here, that is anything but a low angle impactor. This is like you're darn near your 45. How do you know that? Because it's almost like 45 degrees. That's probably how you get that impression, right? But it actually works. So then you come here and you measure that and you're like, whoops. Yeah, okay, and then you go down, you figure it all out. Now it's 50%. Okay, we did that. We made a boo-boo. Ah, there's the real. I was actually able to find B2W. I would tell you if I have no way of knowing what the B2W or what the first blast ring is. Like I told you, I had no way of ever estimating the NPOI in and of itself, because there's no information left for me to do that. So that's why we're using this guy to help us determine the NPOI, right? Because they look so similar, and as it turns out, they really are so similar. Okay, now we go to this one. We're doing all the math. Okay, you can always pause this later if you're a scientist and you want to know how I think. All right, then we go to this guy. Forget all this other blurb. This was the wrong one, and then I had my corrected adjustments made. Showing the math here. So basically, long story short, it actually had a vertical angle of 42 degrees. So when we're looking at the vertical angle, we're actually standing on the pop and looking into space at an elevation that is 42 degrees. Here's the Earth ground, 42 degrees above the Earth's surface, and we're looking into space like that. That's my vertical angle. And so I refer to the trajectory as that same degree, only measured from 0 down. In this case, measured from 0, it's 48 degrees. And you only have 90 degrees to play with to begin with, right? 0 to 90. And you gotta, so if it's 48 coming down from 0, then it's 42 coming up from the planet's surface. And that pretty much narrows that down. Oh my gosh, it's time for me to go. So there you go, folks. That's it for Guacanayabo, and I'll tell you more about other stuff later on. Okay. Make sure you like my site and subscribe, and I got more details to go through. It'll be great to find out about the Hawaiian impactor, a whole entire chain of islands made by a space rock. Pretty scary. Yeah. All right. Bye.